So I want to talk about contemporary relative sea level rise as a coastal hazard. And I think, I want to introduce why I'm talking about this. Um, what's going and now, of course. Oh, there we are. Yes. So, I mean, we're all familiar with the notion of climate induced sea level rise. And here is an image of observations of global sea level rise from about 1880 to the early part of this decade, using sort of combining different estimates of sea level and showing a trend, a rising trend, and actually an accelerating trend as well, so that sea level, climate induced sea level is rising faster today than it was in the past. So this is obviously something that causes great concern. But when we think about sea level at a particular place, nobody lives in the global mean. We all live in a particular place. Then we actually think at a particular location, be it Southampton or East Anglia or Montreal, relative sea level rise is what you see. And that is the sum of all these different components shown here. It's complicated, but if you look at the sort of summary below, global components, that's what the graph to the left is showing. But then there are regional components linked to climatic variability, things like El Nino and and there are also big geological trends. And locally, you get other local changes, particularly human-induced subsidence. And, impacts, I'm interested in impacts and adaptation or responses to these risks. And so we have to think about the relative sea level change and understand that. And so when I was, thinking about these issues, started working on sea level rise a long time ago now, thinking about these subsiding coastal cities, and the poster child really in many ways for subsiding coastal cities is Jakarta, where they are pumping groundwater to drink, and the city has sunk more than 4 meters. So this is a mosque that lies outside the line of defence. So to the right, there's a defence. There's an area that's defended. You can see a sort of concrete vertical wall. That's keeping that area dry, and there's presumably some pumps and things like that as well, because the wall alone won't keep you dry. You need a whole infrastructure system to do that. But this city has sunk very large amounts, and many cities have. And it raised with me the question of, well, what does this mean? We might think about this as a local phenomenon, but what are the bigger scale implications of this? Let's think about this at a sort of global scale and what really it means. And sort of building on this, then, if you go to look at the sort of coastal cities around the world, there's a lot of them, and the number is increasing with time. And we did an analysis a little while ago now. We identified all the cities with more than 1 million people in 2005, and then we looked at the geological setting of those cities, and the ones shown as dots on this map are those which are built on sort of deltaic or recently deposited sediments. So they have the potential to do what Jakarta's doing if you extract groundwater, or if you drain the soils and maybe peat consolidates, etc. So you pick up an awful lot in Southeast and East Asia, but they're all across the planet. I mean, including places like New Orleans, may be quite well known, Houston, or Vancouver, which is built on the Fraser Delta, on the Pacific. And further to that, you can actually see the and I'm sorry, that's it. Yeah, with the cities in Asia, you can see the maximum reported substance that's been observed. So these aren't theoretical numbers. These are numbers from journal papers, reports, etc., about the maximum substance that's been reported in those numbers. So you can see Jakarta 4 meters, Tokyo is 4+ meters, and if you go to the left, you can actually see something about the history of substance from about early part of the 20th century up to 2020, showing how many cities in the region have actually subsided. You can see, interestingly enough, with Tokyo, if you can see, can you see my pointer? Can you see my pointer?
Yes.
Is my pointer visible to the audience? I'm not sure.
Yeah, we can say it, Professor Nicholls.
Thank you. Okay, yeah. So we have Tokyo, which subsided very rapidly. You can see the effect of the Second World War. Substance was reduced because there was less groundwater extraction. Then it continued after World War II. Osaka above has a very similar pattern, and then actually it stops. And what's going on here? I'm sorry, my it's not. Oh, we are, yes. Um, and you see that big change where actually in Tokyo they realized they were losing huge amounts of elevation. Large parts of Tokyo around the docks are now below mean sea level and are essentially like the Netherlands in their need for defense to be dry. So they provided water from another source and they reduced groundwater extraction. They essentially stopped it and they stabilized the land elevations at much lower levels than they'd been before. And you can see that pattern in many of these cities in Asia, although many are still subsiding. Tokyo has been very successful. The others are still losing some elevation. Jakarta, though shown here, is still going down. In fact, Jakarta now seems to have, they may be doing policies in Jakarta as well. So um, you have these areas, these hotspots of substance, but also there are other areas, like deltas are sinking. So what can we say about that? So and when we think about relative sea level rise, um, we think, what are the effects? And you know, the physical effects of relative sea level rise are the same as the effects of global sea level rise. You don't really care whether the land sinks or the sea rises. So all these effects that are in textbooks about the effects of climate-induced sea level rise are relevant with relative sea level rise from subsidence. So you might think, well, the big issue is really you're submerging it, and with those huge changes I just showed you, but that's quite extreme. And where you get slower rates of relative sea level rise, you'll see all the same effects. Increased flooding, erosion, saltwater intrusion, those types of processes. So it has all the same effects. And in terms of socioeconomic impacts, they're generally adverse. I mean, it's very hard to find a benefit of relative sea level rise. It is a negative. It's a negative effect, and you therefore need to really think about, well, how are you going to sort of either mitigate the problem or adapt to it? And that's pretty much the response. And when we look at the coast, we can think of the coast as a system. I was mentioned at the beginning that I like thinking about the coast as a system, but we can think about, we have climate drivers above, so lots of things, sea levels up there in that box, and we have the non-climate drivers below, and substances there. I mean, some substance can be natural. I mean, certain areas are sinking naturally for geological reasons. Then we get these human-induced processes which can really amplify, maybe orders of magnitude, the effect locally. And we get sort of risks, impacts, and we get adaptation. So this is all driving how our coastal areas evolve. And we saw in Jakarta that dike or concrete wall that had been built. So you can see an adaptation that's gone in response there to substance, not really to climate change. And I think, this sort of systemic perspective is rather useful. So I'm going to talk about two papers now for the rest of the talk, mainly, just to talk through how we thought about this in global terms. I mean, I started thinking about this, let's say, a long time ago, and we didn't really have the means when I was first thinking about it. We didn't really have much in the way of global data sets that we really believed to really be able to do this analysis. So in 2021, by that time, we had able to put this all together, and we did a global analysis of contemporary relative sea level rise. And it's quite simple. I mean, and with the next paper that I'll mention, it sort of improved upon that, but it had some quite powerful results. So we took 4 components of the relative sea level change around the planet. We took satellite observations of sea level change, just like I showed you for the global, but we took them obviously on a point by point basis. So that's representing climate change. We took glacial isostatic adjustment derived from one of Peltier's models. So that's predicted, but it's well understood. And I think, the science there is very mature. We took Deltaic substance, we had 117 deltas in our data set. I mean, you can argue about how many deltas there are in the world. We think we have all the big ones. Building on people like Erickson et al. And, deltas naturally subside at 1, 2, maybe even up to 3 millimeters per year. But then it's often enhanced by human activity and also removal of sedimentation to the delta surface. And then lastly, city substance. I've shown you the example with Jakarta, where we also consider the additional substance in susceptible coastal cities situated on deltaic and alluvial plains. And really, we treat these 4 components as independent, so you can simply add them up. There's no interaction, so it's really just a matter of estimating them in space and then summing them. So just looking at the components, just so you understand the kind of data we're talking about. So here's satellite-based observations of sea level change. And you can see that I showed you earlier the global mean. Well, when you actually look at in space, you can see there is quite strong patterns of climate-induced sea level change, because I mean in places sea level has fallen in these pictures as well. It's worth noting it's risen virtually everywhere, but there are places where it's fallen. You've got some blue colors on the map, and you can see, like, for example, very large rises in the sort of Southeast Asia region, for example, as well, in contrast to those areas where sea level is sort of constant or even falling. Then we took the GIA estimates, so glacial isostatic adjustment. So this is the process where the large ice sheets from the last ice age, so thousands of years ago, loaded the crust and actually deformed the mantle. And when that caused a deformation downwards, or and a flow in the mantle. And now the Earth's adjusting to the loss of that load. And so some areas are rising and some areas are sinking. The effect is most pronounced where in the area adjoining where the big glaciers were and adjoining those areas. So in the sort of particularly around the northern hemisphere, in places like North America, it's very pronounced. In the Baltic, but it's a global phenomenon. So, and we have that everywhere. Then we have deltas, and so this data set here just shows the locations of all the deltas. Again, deltas very strongly concentrated in Asia, around the Himalayas, and with the monsoon climate, but they're found all around the planet. And we've color coded those with the deltaic substance, which is derived from the literature. And actually, for many deltas, we didn't really have an estimate of substance, so we just assumed a value of 2 millimeters per year there for those deltas where we didn't know what was going on. So that's just to populate the data set, and then we searched the literature to find better results wherever we could. And then this shows the deltas considered in terms of population. And I think this is quite a powerful sort of picture, because it brings out again that there are large populations. So the bigger the circle, the bigger the population. So you can see that there are large populations in the Asian deltas, and of course Southeast and East Asia really has about 75% of the people living in the low elevation coastal zone. So not surprisingly, the deltas that are located there are also home to a very large number of people. And then the coastal cities that we considered, we had a data set of about well over 100 cities, but in many of them, we didn't have data that they were subsiding. Particularly, it doesn't mean that there might be localized subsidence. I think when you look at most cities, you will find areas that, like maybe areas of reclamation historically that are sinking. I mean, I know I've seen that in New York City, but these areas tend to be quite small. So we're looking for areas where you're getting large scale subsidence of the city, and you can see again big values in areas around Southeast and East Asia. And our method was pretty sort of simple. the literature review, we just drew together the best available information we could. And with the cities, I mean, it's quite difficult. I mean, really, we obviously wanted the average subsidence, wanted the mean. But I think there's a bias where people tend to report the big numbers. I mean, the numbers I showed you before were the maximum subsidence in the cities, not the mean. And so we estimated low and high estimates of additional substance to really understand that. The components are combined using using a kind of global data set, the global framework, the DEVA framework, where we have 12,000 linear segments and a coastline that's about 700,000 kilometers long in this representation that we used. I mean, there's now a new version which is a coastline of about 1.6 million kilometers, but which is much more detailed. But this is the one we used, and to kind of give a sense of what we're looking at here, 6.5% of the world's coast was comprised subsiding deltas or deltas, and about 0.8% of the world's coast comprised subsiding cities, respectively. So they're particularly the cities are a very small part of the coast by length. The global sorry, I've got this. I'm trying to read my slides and I've got something right across it. Yeah, the low elevation coastal zone population is about 768 million people again in the analysis. Depending on the models you use, you will get different numbers. And sorry, excuse me. And as I've said earlier, South and Southeast and East Asia collectively contain about 71% of this population. So 545 million people in 2015. And about, a large number of the global coastal population are living in deltas and or subsiding cities. Relative sea level rise is estimated in two ways in all the analysis I'm going to show you. We do it by coastal length. That's kind of a typical geophysical measure, if you like. I mean, sometimes it's done sea levels estimated by area. What does the average coast see in terms of relative sea level rise? But also I think a more informative statistic is what does the average coastal population see? So it's related more to people, the experience of people. So we weight those areas with lots of people much more highly than those areas with low populations. And to sort of show you the components that are going into this analysis, we go across, there's the climate, component one is the climate-induced sea level rise. Then we have the GIA, the glacial isostatic adjustment, component two. Component four is the city substance, and you can see most places there's not much, but you do get some places where it's rather a large amount of substance, where we're maybe even getting up to sort of 10 centimeters per year of substance. And then the delta substance is shown here in component three. And I suppose the reason they're stacked in this order is actually the slope. This is plotted against coastal population density, and the relationship. They're not exactly linear relationships, but a linear fit is improving as we move from left to right. And then the last panel is showing the summed all components, and cut to the chase, go straight to the result. So what do we find? Well, this is the sort of picture. This is a cumulative frequency curve for relative sea level rise. So you can see the red is the relative sea level rise measured to the by coastal length. The blue is the relative sea level rise weighted by coastal population. So if we look at the red curve first, you can see the median's about 2.5 centimeters per year. And, maybe 12.5% of the world's coast is actually seeing relative sea level fall at the present time. And, as you move up, you can see that a small length of coast is seeing maybe a small percentage is seeing about 10 millimeters per year of relative sea level rise. The blue curve, the one weighted by population, is shifted quite significantly to the right by about 2.5 millimeters per year. So and you can see that although 12.5% of the world's coast is experiencing uplift, it's below zero. This point here, hardly anybody is located in areas where sea level is falling because nobody lives there. So it makes the point about the population weights really change the picture. And so you can see the average person is seeing much more relative sea level rise than the average piece of coast. And this table sort of summarizes the results. In terms of, you can look at the climate-induced sea level rise and the population-weighted sea level rise. And the bottom line is really, it's 2.6 millimeters per year is the global mean for coastal weighting, and the for population weighting, there's an uncertainty because we have this low and high estimate of city substance. We're getting numbers up to 8 to 10 millimeters per year. So maybe 3 or 4 times the rate. So it means, if you like, the burden of sea level rise on people living in the coastal zone is much higher on average than the climate-induced numbers suggest. So I think that's a really very important message. And you can see that in terms of that, you can see the sort of contributions here, so that the deltas and the cities are making obviously a big contribution to the number for coastal weights, while for coastal length weights they're having very little effect. If we look at what the actual components influence, you can actually sort of strip this out. You can see, so the top panel A is showing length weighted, and it shows the climate. Really, you can't see, and the green and the black are the city and the delta numbers. You can see the blue, which is due to glacial isostatic adjustment, and this makes the point, which was apparent, I think, in the table, that actually the glacial isostatic adjustment means that the average piece of coast tends to many areas of coast see lower relative sea level rise than the climate-induced sea level rise, because places like the Baltic or Hudson Bay, these are quite well-known areas. The land is rising very rapidly, and this at the present time means sea level is still falling in those areas. If we move to the population weighting, the GIA really is not having much effect. It's a small effect, and you start to see you certainly see the green and the black lines coming out, affecting more, say, 75% of the coastal population, and you can see that they're very large effect on the values of contribution to sea level rise. So what they're actually contributing. If we look at maps now, we can look at length weights, and we can look at population weights, and we can color code countries by the average relative sea level rise that they experience. You can see basically, if you just go from the length weighted to the population weighted, it goes redder and yellower, I think, just by eye, is quite clear. So you can see that sort of Southeast Asia, so Indonesia really, I think we're looking at really mainly, China come through quite strongly as having quite high rates of relative sea level rise, even based on length weighting. But if you move to the right, you see that they become redder and more orange. So the population weighting is giving you higher numbers. So it really brings out again that region is a hotspot for relative sea level rise in many ways, however you look at it. And you pick up other places, though. It's interesting, like if you look, for example, Italy it doesn't really stand out in the length weighted, but in the population weighted, because we have places like Venice, the Po Delta. There are quite large populations living in coastal plains in Italy, even though so quite a large part of the coastal population is exposed to substance in Italy, for example. So anyway, so I think you get some interesting patterns out of there, and then you can look at I mentioned these three regions, so you can look at the three regions in Asia, and see that the sort of the length weighting values shown here, 4-5 millimeters per year kind of coming out of the analysis. But then when we look at population weighted, it's increased quite significantly, up to sort of 6-7-8 millimeters per year. But in Southeast Asia, it's going up to more than above 10 millimeters per year. In fact, up to 25 millimeters per year for the average person. So that's rather dramatic. We can also, deltas are known to be very vulnerable to sea level rise. So that was recognised from the very first time that we started assessing impacts of sea level rise. Deltaic regions were often distinguished. We can also look, small islands were also recognised as being incredibly vulnerable. There's the population. If you look at the population of these deltas is in the hundred. These Asian regions is in the hundreds of millions in the low elevation coastal zone, which is below 10 meters elevation. Very high densities. The small islands are also extremely vulnerable. We're talking about though much smaller populations of people. I mean, often, sort of in the millions sort of mark. So, and you can see that for these regions, the effects we're talking about here are not really relevant, because then these islands don't subside. So just to give you the counterfactual, really, that obviously you've got it's something that's varying in space. And then we've actually, so we got this analysis, and then lots of new data is becoming available, and new methods. So we have satellite platforms like INSAR, which uses altimetry to measure the vertical deformation of to infer the vertical deformation of the Earth's surface. There's GNSS, sort of GPS systems as well, which are linked into sort of geodetic networks. We have people that have been doing synthesis of vertical land motion in areas that are due to tectonics, which is not really considered in the paper that I just presented to you. But we do know that, for example, we get areas with earthquakes, and so we get uplift, and we get substance both abruptly in earthquakes, and in between we get changes. So there's a whole type of change, and so this paper really tries to bring that together. Julius Oselman, the first author, actually his work has been very much on trying to understand these vertical land motion at the global scale. So we're synthesizing in the data set that he developed when he's still working on it, the data set he developed in his PhD, and really merging these and bringing in lots of new kinds of measurements. So and this was published literally 2 weeks ago, so this is a very new paper. So first of all, so we're talking about a hybrid estimate of vertical land motion. I suppose before we had a hybrid estimate, but we're trying to draw together the best data we can everywhere, and we draw in the sort of GNSS and INSAR data I've already mentioned. And if you look down here at these two pie charts, you can actually sort of see what the percentage of population covered either by population or by coastal length. And you can see here INSAR covering, it gives you a coverage of nearly 65% of the coastal population. GNSS is a relatively small number of people. GIA models, relatively small. And vertical land motion from Julius's work covers the rest. And when we have similar, so we're bringing together these different data sets on a map. You can see the areas that have black rings around them are where we have INSAR data. So INSAR data doesn't cover the world's coast yet, but the people have done the analyses have focused on deltas and cities because they're so important. So they focus on where people live. So in terms of this population weighted view of the world, they're giving us data where we most need it. In places like Europe, or North America, and certainly the US, we have global. We have complete coverage of the coast for those parts of the world, and of course this is improving with time. So we'd expect to be able to do a much better analysis in the future. And over here you can sort of see some of the data from places like this is the Nile Delta. So anyway, we move on now to, and so what is the vertical contribution to sea level change? And this map here shows areas that have the relative sea level change that's happening in millimeters per year. So red is showing it's going down, so it's relative sea level rise. Blue, it's rising. So we see again, say Hudson Bay, northern Canada, the land is rising, or Chile here, for example, or parts of the Pacific coast of of Canada and Alaska. But we see that there's actually a lot more red on here. You can also see the population as well. The sort of color coding is giving you a feel of where there's lots of people moving here. Maybe this is the interesting sort of plot really that sort of summarizes the global results. So this is an axis. This isn't relative sea level rise. This is vertical land motion. So if you wanted to include make it relative sea level rise, you'd have to add the climate-induced sea level component to this, which would move these curves to the right a little bit, 2 or 3 millimeters per year, depending on the time scale when the data that you used to cover it. And what you can see, the blue is the length weighted, so it's exactly the same as the previous analysis. So there's a length weighted estimate of VLM. So it shows that probably about half the coast by length is experiencing negative vertical land motion. The land is rising relative to a geodetic datum. Okay, so, and the other half is falling relative to a geodetic datum. But if we move then to the red plots, then we can see, well, if we do population weighting, what do we see? And well, the curve, the curve moves to the right, just as it did in the previous analysis. And we can see that 71% of the world's population is living in areas that are experiencing vertical substance. The vertical land motion is positive and the land is falling. And then say 55% are experiencing at least 1 millimeter per year, and 43% are experiencing at least 2 millimeters of substance per year. So that's bringing out the point. We're getting quite similar results. And actually, if you look at the dashed line, the dotted line is actually from the earlier paper. So you can see that this new analysis actually has a bigger tail of areas with uplift. So we weren't picking that up in our earlier analysis. So that's doing a better job there of capturing the areas where we're getting uplift. But most of the curve is quite similar, except maybe for some of the very high values. And I think we're getting there into the terrain of those cities where we were recognizing that we know there's always a danger of bias when you were looking at the literature. While this is obviously, this is direct measurements with INSAR of how those cities' elevations are changing. And then we can look at the different VLM components. And if you look at B, maybe this is the sort of the key plot. Blue again is coastal length weighted. Red is population weighted. And for the relative sea level rise, you can see that the numbers here, we're getting at least the average person having 6 millimeters per year of relative sea level rise. So a little bit lower than the other paper, but based on much better data, and it's not complete. So I mean, so again, there's an uncertainty there as well. So I think the key and in terms of the length weighted, it's about 3 times the length weighted is about 2 millimeters. So it's about a threefold amplification. If you look at absolute sea level rise, it's about twice the absolute sea level rise, because when you transform the absolute sea level rise to relative sea level rise, you actually the GIA tends to reduce it around the world's coast. So you're seeing the same effect as we saw in the last paper. So I think this is really this is great to be able to move on to a more robust analysis, which again really confirms the point that relative sea level, the average person in the coast is seeing higher rates of relative sea level rise. So what do you do about this? Well, when we think about relative sea level rise, climate change, whatever, but also due to substance, we can think about coastal adaptation measures. And outlined here are all the different adaptation measures that can be considered. And this comes sort of straight out the IPCC. We can move, we can put our houses on stilts, whatever. We can build barriers. That's what we saw in Jakarta. Or we can even advance. I mean, you can fill. The island to the right here, Hulamali, is an artificial island in the Maldives, and it's been built a meter higher because of climate-induced sea level rise. So it's not substance. So but I'm just making the point about the strategy that you can raise land areas, and obviously, with substance, you can also think about mitigation. With climate change, we think about mitigation of greenhouse gas emissions. So we try and remove the source of the problem. With if substance is human produced, we can think about mitigating that, removing that source. So we can have substance mitigation, or we can use the word substance control. I see them essentially as synonyms. And going back to the earlier paper, we did sort of look at this over time, looking at exposure. And the key plot here maybe is, you can see building up, we have no vertical land movement. We bring in GIA, in delta substance, and then we bring in GIA, a delta substance, and city, assuming it's not controlled, and it continues to 2050. So it's a scenario, it's a thought experiment, and you can see that the numbers of people exposed rises. It's the big effect that really is increasing the exposure. And then in E, well, let's imagine you can reduce that substance to 5 millimeters per year, which, based on those plots we showed earlier, Tokyo has stopped it altogether, but you maybe can't stop it completely, but you can really greatly reduce it. And that can have a huge effect in terms of reducing exposure. So I think really substance control is something that really needs to be thought about much more. Can't blame everything on climate change. Climate change is a problem and it needs to be addressed. But here in many of these places, we have the sort of two things working together, and we need to think about them in a more holistic way if we're going to really solve these problems in an efficient manner. So concluding remarks. So average coastal sea level rise was around about 2.5 millimeters per year over the last sort of 2 decades. However, coastal inhabitants experience a much larger average relative sea level rise, and that's estimated by Ulsman et al. To be about at least 6 millimeters per year. So it really means that I think people concentrate in areas that subside, and therefore the risks and response needs to relative sea level rise are larger than kind of global mean changes due to climate alone would suggest. So that's an important message. That's an important message to people like the IPCC. It's an important message to people like the World Bank and the Asian Development Bank. It's an important message to people like the insurance industry, who, anybody that owns risk distributed across the planet needs to understand this fact. I think, human-induced substance needs much more regional and global consideration. And, I think responding to this, responding to substance and responding to climate change are entirely complementary. There's no conflict between them. They're both about reducing risk. However, when we look at this, I think our understanding and knowledge on the geological components of relative sea level rise remains fragmented. It's still studied really by lots of it's studied rather separately. I'm at a meeting here on climate change, and we've made that point that the climate community is very integrated. The community dealing with subsidence is not. And so that's something that probably needs to be focused on in the future. But the kinds of questions that need to be asked is, what is relative sea level rise today? Observations. I think, with the work I just showed you, that new paper, we're getting much better observations. So we are understanding much better what's going on, but there's still a long way to go there. It's certainly not done. What are the components and what are their causes to attribute the changes? So you can measure a change. Why is it happening? Is another question, and it needs more knowledge to really understand that, because sometimes there's two or three things going on at the same time. Then a key question, what might relative sea level rise be in the future? So there you need a model framework. You need some way of predicting what's going to happen. I mean, we simply projected the trends we just linearly projected the trends. That's a very simple model, probably not terribly good, but as a thought experiment, we want to get more realistic views of what might happen that help people make better decisions. And then what can we do about it? And I think, we can think about mitigation and substance and control, and we can think about adaptation. But I think, so really, this is a sort of an area of work where it's a local problem, but it has global significance. And so I think it needs to be addressed by the global community in parallel with addressing the threat of climate-induced sea level rise. So with that, there's the sources. I'll happily take any questions.